Good morning. Last lecture we saw how we got a modified member force deformation relationship. This lecture I'm actually going to take you through one problem completely so that you can understand what it is that this involves. Okay? And I'm going to take a frame problem. Let us take the problem. Time before last, we looked at some kinematic relationship. So I'm going to take that same problem, excepting that I'm going to make one of the okay. Under normal circumstances, you will see that this has 2 degrees of freedom. 1 degree of freedom is this lateral displacement, and 1 degree of freedom is the rotation at this hinge. However, since this is an end hinge, I am going to consider this AB member as a modified member, so that I will write down the modified member force deformation relationships. For BC is rigid. This is EI and this is also EI. This is totally rigid, flexurally as well as axially. These are actually rigid but flexurally flexible, so is this one. Okay, and this is being subjected to this load, and the question is bending moment diagram. That is what has been asked today. Okay. Note, last time I had said that since member BC is a rigid member, you cannot write down a member force deformation relationship because deformations are 0. So you cannot write down a member force relationship. However, you can write it for AB and CD. Okay. So now the first thing is that let me write down the member force relationships. First, okay, let me go through it in an algorithmic state, just like I had done for force method. What is the first step? Identify number of degrees of freedom and identify the degrees of freedom. If the degrees of freedom are related to a hinge, end hinge, then we can forget those degrees of freedom. Those are non-essential degrees of freedom. Okay, so although this is a 2 degree of freedom, you can evaluate it to be a 2 degree of freedom. This is a non-essential degree of freedom because the moment at this point is equal to 0. Okay, so we have only one essential degree of freedom. So this is a single degree of freedom structure. Okay, fine. So once having done that, next step is to write down the member force relationships for each member. Okay, for member AB, what do we have? We have this situation. Okay, so this is A, this is B. So what is the member force deformation relationship? You're going to see that it's only going to be MBA and theta BA, and so this is going to be equal to MBA is equal to, note that none of the members have any member loads, so this is going to be equal to 3 EI upon L theta BA. That's the only member end. For BC, since it's rigid, you cannot write down force deformation relationship because deformations are 0. So for this you cannot evaluate BC. There is BC, there is CB, but we cannot write down any force deformation relationship for this. And for CD, since it's fixed, the member end deformation becomes, and here note that I am using the modified definition of theta b, so it's going to become equal to plus 2ei upon L theta dc. I am not putting the additional because this definition of theta CD is from the chord joining C to D to the displaced tangent, same as this. Okay, and M dc is equal to 2EIL theta CD plus 4EI upon theta dc. Okay, so this is my these are my member. There are 3 members, AB, BC and CD, and these are my member force deformation relationships. Okay, so now next step is to relate the member deformations with the structure displacement. How do I do that? Kinematics. What do I do? Well, I write down this is my structure, and what is my displacement? I am going to put delta equal to 1. So delta equal to 1 means, see, if you look at this, that means all that delta equal to 1 means is that this point has to move horizontally by 1. Now can this point move vertically? No, because since this point cannot move anywhere, if this point were to move vertically, that would involve axial deformation. So this cannot move vertically, so this would only move horizontally, and therefore this point we know where it is. This point is at a distance 1 from where it is. Now let's look at this. Left to itself, this would go 1 this way. However, this point cannot go anywhere, displace. So therefore this point can only move along its tangent. And if it moves along its tangent, this member also can move along its tangent, and this is the point. Okay, and this we've already looked at last time, lands up being this. So this is where your point B has gone. Now since point B has moved here and C has moved here, now this member has to remain straight because it is a rigid member. A rigid member can only go straight, and since this angle then it becomes 3 upon 4 divided by 15, so this becomes 1 by 20, and therefore this, the tangent over here automatically has to follow this. Okay, so this becomes like this, and this tangent also has to follow that, so this also becomes, this is 1 over 20, this is also 1 over 20, so this goes. Note that since here it's hinge, it's free to rotate, so it will rotate in this fashion. Okay, so now note that to find out the from the chord, I need to actually connect these joints up, because this is A, this is the displaced position of B, so I'll call it B prime, this is C prime. A and D, A prime and D prime are exactly where it is because these are supports. Okay, so this is going to be in this fashion. The angle this is going to be equal to 1 upon 12. So is this angle going to be 1 upon 12. Similarly, this angle is 5 upon 4 upon 15. 5 upon 4 upon 15 becomes 1 over 12. So this is also 1 over 12. And so therefore, now having drawn this, we need to put down what these are. So theta AB we are not interested in because again remember that in AB, member AB, the only member in different relationship is MBA equal to theta BA. So keeping that in mind, we only need to know what theta BA is. So theta BA is 1 by 12 plus 1 over 20. So this is equal to, in terms of 65 plus 3 is equal to 8 upon 60, which is equal to 2 upon 15. Is it positive or negative? From the chord to the tangent, it's positive. What is theta BC? Note again that I don't need to find out theta BC and theta CB. I know that they are 0 because from the chord these are 0. So I know those. They are rigid. There can be no deformation. So I'm interested in finding out theta. See, why do we find these out? So that we can relate. See, we can relate all these in terms of the delta. That's the reason why we find this, this and this. These are the only 3 that are there. So we only need to find out these 3. So when we find out those 3, theta CD is equal to, you will see that again 1 plus 12 plus 1 plus 20. So that makes it plus 215. Again anti-clockwise, and theta DC is equal to 1 by 12. So having input these, what do I get? I plug this into the original equations and I get MBA is equal to, and what is L for AB? It's 15 into theta BA is 2 by 15 delta. Okay, MCD is equal to 4 EI. What is CD's length? 12. And theta CD is equal to 2 by 15 delta plus 2 EI upon 12 into theta DC. Theta DC is 1 by 12 delta. So if you look at this, this essentially becomes this becomes 6 EI delta upon 225. This becomes 1 upon 12, and inside you'll get EI delta. I can take EI delta outside, and inside I get 8 upon 15 plus 1 upon 6. So this is going to be equal to, this is going to be 30 is the nearest. So 30 would make it 16, and this would make it 5. So 21 upon 30. So this would become 21 EI delta upon 360. Okay, which if you look at it becomes equal to 7 EI delta upon 120. Okay. So that is MCD and MDC is equal to 2 EI upon 12 into 2 by 15 delta plus 4 EI upon 12 into what? Into theta DC. Theta DC is 1 by 12 delta. So if you plug that in, you get again EI upon delta 12 outside. Inside you get 4 upon 15 plus 1 by 3. So this becomes 4 plus 9 upon 15. 9 upon 15 becomes 3 upon 5. 3 upon 5 becomes EI delta upon 20. Okay. Note all of these are positive for delta. Okay. So having obtained these, now what's my next step? My next step is actually write down the equation by taking this as my virtual displacement. I'm going to use the principle of virtual displacement where this is my virtual displacement. Okay, I can put any arbitrary virtual displacement, so I opt to put virtual displacement equal to 1. So what is the work done by all the forces? Let's see. Work done by all the forces are equal to, what is the work done by the external force? It's going to be equal to 1, since unit virtual displacement into real force. The real force is 20 kilonewtons. What is the internal virtual work done? Internal virtual work done is going to be equal to theta BA. That is the virtual theta BA is going to be 2 by 15 into MBA, the real moment, plus 2 by 15 into MCD plus 1 by 12 MDC. Okay, so MBA, so this one then becomes equal to, if you look at it, 2 by 15 multiplied by 6 EI delta upon 225 plus 2 upon 15 multiplied by 7 EI delta upon 120 plus 1 by 12 into EI upon 20. Okay? So, now this, if I take it through, you will see I'm going to just see this is equal to this. So all I'm going to do is I'm going to multiply by 15 both sides. So this will become 300 is equal to 12. And now I'm going to take EI delta outside. So inside becomes 12 upon 225 plus 14 upon 120 plus, now if you look at this, 240, this is 240. If I take off 15, I've taken 15 out. So if this goes into 15, 16 times. So this is 1 upon 16. Okay. So if we take, please make a note that this will actually go 4, and this becomes divided by 3 becomes 75. Okay, so 4 upon 75 plus 14, this becomes 7 upon 60. Okay, so this is 15 into 4 and this is 15 into 5. So we're going to have LCM is going to be equal to 15 into 5 into 4 into 4. Okay, so this is going to be equal to 4 cubed, so that is equal to 64. This is going to be equal to 20, so that's 140, and this is going to be equal to 75. Okay, so this is equal to 204 279 upon, this is 20, 80 into 115 is 1200. 204 279. So this is going to be equal to, this can be divided by 3. So this will become 3 is going to be equal to 93 upon 400 EI delta. Okay, so delta is going to be equal to 12 4 zeros upon 93 EI. Okay, now so I know I found out delta. So once I found out delta, I can substitute back into MBA, MCD and MDC to be able to evaluate those values. Okay, and how would my equation and then how would my boundary, how would my this thing look? So if you see, is this positive? This is positive. So if these were positive, that means MBA would be also positive. Okay, so MBA is positive, MCD is positive, MDC is positive, which are equal to, if you look at it, 2 upon 75 EI delta. Okay, so which basically means 2 upon 75 into 1200,000 upon 93. Note that EI, this is also EI, so EI cancels, so this is the value of MBA. MCD is equal to 7 EI upon 120. So this is going to be equal to 7 upon 120 into divided by 93. And MDC, which is equal to EI delta upon 20, is going to be equal to 20 goes into this thing, so it's going to be 6,000 upon 93. Okay, so these are the values. Unfortunately I do not have a calculator, so but you should be able to obtain these values. Okay, this one also becomes, so I can say, I can put down some values over here. This will go 25 will go 3 times, and this will go 25 is going to be 4800. So 4800, also this goes, so this is 1600. So ultimately MBA is equal to 3200 by 93. Okay, MCD is equal to 7000 by 93, and MDC is equal to 6000 by 93. These are kilonewton meter, kilonewton meter, kilonewton meter. Now what is MBC equal to? You see, because what we have done here is we have, let's look at this. MAB I know is 0. I found out MBA, okay, I found out MCD, and I found out MDC. What do I need to find out? I need to find out what MBC and MCB are. What are MBC? Well, note that from equilibrium, MBC has to be equal to minus MBA, and similarly MCB from equilibrium has to be equal to minus. So therefore, if you look at this particular situation, okay, this becomes, approximately this would be about, say, about 35. Let's just put down some numbers. Approximately 35. This is going to be approximately about 14, about 7, this is 13. So 13 will be about 78, and this would be about 15.5. So this would be about 60. Or thereabouts. Okay, so therefore the point here to note is that so once I know this, so if I look at the bending moment diagram, how would the bending moment diagram look? At this point this is 0 and this is anti-clockwise. So if you look at this, the bending moment diagram will look like this. Okay. Now let's look at this. This is anti-clockwise. So since it's anti-clockwise, it's going to be drawing it on the compression side. So this is going to be this way, and this is going to be this, okay, and over here. Over here, this is this way. Over here, this is this way. Over here, this is this way. And over here, this is this way. The values, this is 3200 by 93 kilonewton meter. Both of them. Here, both of them, the value is 7000 by 93 kilonewton meter, and over here is going to be 6000 by 93 kilonewton meter. This is my bending moment diagram for the 20 kilonewton force over here. Okay, so you saw the steps. Okay, the first step, identify the degree of freedom. Next step, write down all the force deformation relationships for all the members that are possible. Third, get the kinematic relationship between the member end deformations and the structural degree of freedom, displacement corresponding to the structural degree of freedom. Then use the virtual work equation and write down the equation corresponding to each structural degree of freedom. Solve for the displacement corresponding to the structural degree of freedom. From that, derive the member end forces. Once you've got the member end forces, you've got a structurally determinate member. You can draw the bending moment diagram for each member, put it all together, and you have the bending moment diagram for the structure. Okay, this in essence is your what am I call it? Displacement method. Okay. Now, what I'm going to do is I'm actually going to sit and look at another problem. The reason behind that is very simple, because the overall scope of what we want to do is that you have to understand what are the various ways of tackling this problem. How do we apply virtual work principle? How do we get the member and kinematics? You see, these are the two fundamental points as to in the whole displacement method. Okay, how do we write down? See, how do we choose the members? Because as I said, normally all members where the two joints at the two ends are continuous joints, you will always have a fixed member. So the member force relationship is very simple. If you have a member load, then you have to compute the fixed end moments. If you don't have a member load, then you don't need to compute the fixed end moments. Okay. Next is, if you have one end of a member which is a support, and that support is a hinge support, we can eliminate that degree of freedom and modified beam, so that the modified member force deformation relationships. And once you've done the member force relationship, the next step is the kinematics, the relationship between the member. So you essentially apply each displacement corresponding, unit displacement corresponding to each degree of freedom, and see how the structure deforms. And from that, evaluate what the member end deformations are. This aspect is called kinematics. And once you have the kinematics, then applying the virtual work principle becomes reasonably simple. The only point that I would like to make is that for each kind of situation, you need to consider, every case becomes different. For example, if you don't have member loads, then you don't need to consider any additional forces. But if you have member loads, then in the virtual work equations, you actually need to put in how much deflection the reactions are undergoing, and that will give you the overall scope of the virtual work equations. And once you've got your virtual work equations, then it's a simple algebraic matrix solver to get all the displacements corresponding to the degrees of freedom, and then substituting back, you get the member end moments. Once you get the member end moments, you should be able to draw the bending moment diagram, shear force, everything. You should be able to find it out, because statically every member becomes a statically determinate structure. Okay, so now what I'm going to do is I'm actually going to take you through one or two problems to show you how to tackle this problem. Okay, and for this, let us now look at this situation. This is the structure. Okay, I'll keep choosing different structures. So this is the structure, and under these loads, I have to draw the bending moment diagram. That is my question. So my question is, and I also wish to know another additional point. I wish to know how much this support displaces by under these loads. Okay, so that's also another point that I would like to know, my delta. Okay. Now, from this point onwards, I'm going to stop using theta B, theta C, delta the way I've been using till now. I'm start going to defining the structure degrees of freedom using a notation R. So in other words, suppose I have 3 degrees of freedom in a structure. I'm going to call them R1, R2, R3. Now R1 may be a rotation, R2 may be a displacement, all that does not matter to me. I'm going to define them as displacements corresponding. Now if the displacement happens to be a rotational, rotation is also a rotational displacement. It's a general displacement. Just like when we say force, I mean not only a linear force, I also mean a moment. Okay, so this is the problem. Now I'm not going to be able to solve this problem today. So what I'm going to take you through is some of the basic parameters, so that next time when we meet, we can actually try to go through the solution process. Okay, so let us see what are the first steps. First step, and let me write this down so that it gets it into your head, that this is the displacement method. One, determine kinematic indeterminacy, which is equal to the number of degrees of freedom. That is the first step. To identify the degrees of freedom. In other words, identify the displacement quantities that you want to be your degrees of freedom. Normally, this is self-explanatory. In peculiar situations, you may have to choose this. 3. Write member force deformation relationship for each member in the structure. The assumption over here that we are making, we'll release that much later. Right now, just for simplicity, the assumption that we are making is that each member is considered to be actually rigid. So I'm going to write that down. Implicit, it is not required, but we are making implicit assumption axial rigidity. This is implicit. Okay, so therefore the force deformation relationship essentially becomes moment rotation relationships. Okay, now you may not be able to write this if a member is flexually rigid also, just like we saw that previous you had member BC which was flexually rigid. We could not write the member force deformation relationship for that. Okay. Fourth, is, see, for one of the things is right member force member relationship. Before that, actually, this is 3b, 3a is identify for each member whether it is standard or modified. Okay, this is important. Why? Because just like we showed that if you have a situation where you have a member whose one end is a hinge support, then we can use the modified. Okay, and then we write the appropriate member force deformation. See, now first important step over here is this: determine kinematic number of degrees. After that, identifying the degrees of freedom are not that important. And once you identifying the force deformation relationship, standard or modified, is also easy. Writing down the force for each is also easy. Okay. The fourth step, before that, the fourth step should be obtain expressions for fixed end moments if member loads are present. Okay, so if you have member loads, then you need to do this. If the loads are at joints, then you don't need to do this. Next is kinematics. This is another very, very important. The entire success of your displacement method actually depends on the kinematics. If your kinematics is wrong, your solution process is going to be wrong. Okay. Next step is the virtual work equations for each degree of freedom. How do we guide down? We take kinematics. For each degree of freedom, we find out the displaced shape, and that is the kinematics. Find displaced shape for displacement corresponding to each degree of freedom. The next important step is the virtual work equations for each degree of freedom. There are some considerations that we will show you over and over again which go into this. Seventh, solve equations to get displacements. 8, obtain member and moments. And once you know member and moments, then you can get. So this in essence is the displacement method. Okay. So once you have this displacement method, let us go through some of the steps for this particular problem that we have identified. Okay. First, degrees of freedom. Determine the kinematic indeterminacy. How do we go about it? 1, 2, 3. How many degrees? Joints are, so unrestrained degrees of freedom are equal to 3 into 3, 9. How many restraints? This is a fixed. So in a fixed you have 2, and this is a fixed roller. In other words, this cannot move in this direction, it cannot rotate, but it can displace this freely. So how many are we constraining? We are restraining the rotation as well as this motion. So there are 2. So 2 plus 2. So restraints is 2. Constraints, are 2. So minus 2. How many does that leave us? That leaves us with 3 degrees of freedom. What are those 3 degrees of freedom? They are, what are they? Let's go back. Let's understand what these are. One is the rotation, theta b. This I will classify as my R1. Remember I was saying I was going to use, so theta b, I'm going to call that as R1. Okay, what else? The delta at C. So this I'm going to classify as my R2. What else? Okay, let's see what happens. Suppose I stop this from going up. Okay, can this go up and down? I've made a mistake here. 3, there's 3 restraints here and 2 restraints here. So that's 5. So 9 minus 5 minus 2 is 2 degrees of freedom. Okay. Now, here the point to be noted is this, that there is, let's look at this. Can this rotate? This can rotate. If this displaces upwards, what happens over here? Okay. If you look at it, that this joint can rotate in any direction that it wishes, okay, because AB is constrained to move. Okay. So you have 2 degrees of freedom. We have identified 2 degrees of freedom for this structure, and then what is the next step? Next step is, we also identified the degrees of freedom, we've determined. So we've completed the first 2 steps of the displacement method. Okay. The next is to identify for each member the force deformation relationship. Is whether it is standard or modified. Is any member hinged? No, it's not hinged. So therefore, both AB and BC are standard members. So 3A has been completed. What is 3B? 3B is right member force deformation relationships for each member. Is that going to be for AB and BC? Both of them are going to be 4EI upon L into the theta at that point plus 2EI upon L. We already know that. So those are the member end. Obtain expressions for fixed end moments. Does AB have any load on it? No. So fixed end moments at A and B, AB and BA are 0. Does member BC have a force on it? Of course. So we have to determine fixed end moment B and fixed end moment at C. Okay. So we will do that. We will do all of this in my next lecture to you. Okay. So thank you for listening to me, and I hope at the end of this lecture you are reasonably clear as to what are the steps that are involved in a displacement method. And over the next few lectures I'm going to solve different problems and show you how the different considerations that come into the aspect. 1. Determining the kinematic degrees of freedom. 2. The kinematics. And 3. How to write down the virtual work equations. These are the 3 important points, and each problem that I'm going to be looking at will have a different aspect to all these 3 points. Okay, thank you very much. Look forward to seeing you next time. Bye.